the main focus of my work is cosmology with dark sirens. That is, gravitational wave binaries that have been detected without an electromagnetic counterpart. So the main sort of overview for today, which I'll run through very quickly, is why we want to use gravitational waves for cosmology in the first place, and a quick overview of the methodology for doing so, methods of dealing with galaxy catalogue incompleteness, and then a discussion of some of the challenges that come with handling real gravitational wave data and real galaxy catalogues. Then how population and cosmological parameters intertwine and are actually very linked, which I think will be of particular interest. And then finally, looking at the current state of affairs, where we are in the field and where we're probably going to be going in the next few years. So in the very beginning, why use gravitational waves for cosmology? In case anyone is rusty on their cosmology, I'm talking specifically about the Hubble constant at the moment. As we're all aware, the universe is expanding. The rate at which it is expanding is known as the Hubble constant. And if you want to measure the Hubble constant in the local universe, you can use this equation here on the left-hand side to do so. Essentially, this is saying the only ingredients you really need to make a measurement of the Hubble constant are a luminosity distance and a redshift. And from those two parts, you can measure the Hubble constant. A lot of people have already measured the Hubble constant in a variety of different ways, and getting increasingly better precision as they go on. But something very interesting is appearing the better these measurements get, which is represented in the right-hand figure here, which is that measurements made using early measurements, which are sort of high redshift measurements, tend to favor lower values of the Hubble constant, while local measurements, also known as late time measurements, tend to value higher values of the Hubble constant, and there is a growing tension between these two values as we see them. Currently, it's not known if the cause of the tension is due to systematics potentially impacting the local measurements, where astrophysics kind of makes everything a bit messy, or whether there is a problem with the cosmological model which is being used for these early time measurements, which is meaning that the value of the Hubble constant they predict doesn't match the one that is being measured locally. So what would be really nice would be to be able to provide an independent way of measuring the Hubble constant that could potentially arbitrate between these two cases by agreeing with one sort of set of measurements or the other. And this is where gravitational waves come into it. Because as I'm sure many of you are aware, one of the direct sort of measurables from a gravitational wave signal from a compact binary is its luminosity distance. It's encoded directly into the amplitude of the gravitational wave signal, and it doesn't require any external calibration in order to get that value. So a measurement of the Hubble constant with gravitational waves would be completely independent of any of the other measurements that are shown here. The only other thing that we need in order to do this is obviously the missing redshift piece, but that's slightly more problematic because any redshift information in the gravitational wave signal is degenerate with mass, which complicates things, and so the redshift information has to be found in a different way. Now, the most obvious way to do this is a very simplistic flowchart of how one might go about doing cosmology with gravitational waves. You detect a merger, and it undergoes parameter estimation to give you a sky localization and the luminosity distance. If you detect an EM counterpart, are so lucky to do so, you can measure the Hubble constant directly using that, as was done with the binary neutron star GW 170817. The EM counterpart was associated with its host galaxy, and the redshift of the host galaxy was then used for the measurement, providing a very informative result for a single data point, although obviously not informative enough to actually start to arbitrate which side of the tension our measurement will fall on. That said, we have now had 3 full gravitational wave observing runs, and so far that is the only electromagnetic counterpart that has been confirmed to be linked to one of the gravitational wave signals. So we have a lot more dark sirens than we do bright ones. And one potential way of using these dark sirens for cosmological measurements is to use galaxy catalogues to provide the potential redshifts of the source. So this idea was suggested by Schutz back in the 80s, and essentially it requires identifying all of the galaxies within the localization volume of your gravitational wave event, treating them all as potential hosts, and then marginalizing over them. The idea is that the true host galaxy will be in there, which will give you the real value of the Hubble constant, and all of the other galaxies distributed at random redshifts will give you other random values of the Hubble constant. And as you combine multiple events together, the true value of the Hubble constant will stack over time, while the rest of these will statistically average out, allowing you to form a constraint. However, that makes it sound very straightforward, and it is anything but. One of the things that I will be talking about today is how you deal with galaxy catalogue incompleteness. That is the fact that galaxy catalogues sadly do not contain all of the galaxies in the universe, and therefore there's some possibility that the host galaxy will not be contained within them. And the other side of the difficulty, which I'm sure many people here are very, very familiar with, is correcting for gravitational wave selection effects. The fact that we have detectors which are not infinitely sensitive, and so are more likely to detect certain kinds of events than others. So first of all, here's a sort of Bayesian framework that this work is carried out under. I think hopefully everyone is fairly familiar with Bayesian notation at this point, but if you're not, this term here on the left-hand side is the posterior probability on the Hubble constant, the thing we want, given a set of gravitational wave data. That's this XGW here. And the other thing on the right-hand side is DGW, which denotes that for each of these XGWs, we have detected the gravitational wave event, i.e. we are only considering things which passed some detection threshold. The right-hand side breaks down into sort of more or less three parts. There's a prior on H0, which we shall just assume to be uniform and ignore for the time being. There is a rates term, the probability of detecting n gravitational wave events for this value of the Hubble constant, which does depend on the Hubble constant, but if you take a prior of 1 over r on that, the Hubble constant dependence drops out. So I will also be neglecting this term for the time being. And then that just leaves us with the final term, which is a product over your gravitational wave data. Essentially, you can break down the analysis into a sort of piece-by-piece, event-by-event analysis, and then multiply the likelihoods from each event together at the end to get your posterior on the Hubble constant. So if we look at this a little bit closer, you can Bayes this expression for one event, and it looks something like this. Now, the first term handily goes to 1 by definition. It's probability of detecting a gravitational wave given said gravitational wave data, which we already know by definition has passed the threshold. So this leaves two other terms: the numerator, which contains the gravitational wave information specific to that event, and then the denominator, which basically constituents gravitational wave selection effects. And this basically acts as a normalization term. And because it depends on the Hubble constant, it's not a normalization term that we can neglect. So what are gravitational wave selection effects? Essentially, just that our detectors aren't sensitive to everything. We are more likely to detect things which are heavier, which are nearby, or which are face-on. All of these things make events more detectable. And essentially, if you want to compute it, you can integrate over all possible gravitational wave signals from a population and basically ask what fraction of these are likely to pass your threshold for detection. So like on the right-hand side here, for population of binary neutron stars, probability of detection as a function of luminosity distance might look something like this, where you're very likely to detect things nearby, but by the time you get out maybe 200 megaparsecs, the chances of you detecting anything are fairly low. The way to compute gravitational wave selection effects, sort of this term here, I'm sure other people will talk about this in more detail, but theoretically you could generate a bunch of sort of mock data or mock events, and for some setup with some detector sensitivity, ask, is this event going to be detectable, yes or no, and sort of build up, compute it in a sort of Monte Carlo fashion like that, which sounds simple enough, but is going to prove to be very tricky. And I will come back to that more towards the end of the talk, but as a hint, it does become more complicated when dealing with binary black holes, for which the populations are rather more uncertain. So for the time being, we'll go back to our method, our framework. And this is basically to show what do you do, how does the galaxy catalog that you're using to provide your prior redshift information actually enter the analysis. So you can expand this term to look something like the right-hand side, which I've handily color coordinated. Essentially, if you have a galaxy catalog which is complete and does contain all of the galaxies, your computation reduces to a sum over all of the galaxies in that catalog. Essentially, you're evaluating the gravitational wave data, the probability density at the redshift given a Hubble constant and sky location of each galaxy. This term here means that you can sort of incorporate some gravitational wave merger redshift dependence. So if you believe that gravitational waves were more common at higher redshifts, then you can include it in this term here. And then there's also this final term, which refers to luminosity weighting, i.e. the probability that a galaxy that is perhaps more luminous might be more likely to hold a gravitational wave event. More luminous things tend to be more massive, and so it's a fairly logical step to say that perhaps they're more likely to host a gravitational wave binary that would then merge. And so if you want to include weighting of that kind, it can be incorporated in this way. And then the denominator is very similar, except instead of the gravitational wave data for a single event you're evaluating, it's the probability of detecting a gravitational wave source from a galaxy at that redshift and at that sky location, effectively. And so if you do this, you can sort of build up an estimate of the Hubble constant. So this is an example using 250 mock binary neutron stars that were simulated with an O2 observing run 2 like sensitivity for 2 detectors. And basically what you can see here are the individual event likelihoods with the thin lines, and multiplied together gives you the orange posterior, and with the dashed black line being the value of the Hubble constant that was used to generate the data in the first place. And the thing to note is that the majority of your individual events don't actually peak at the value of the Hubble constant, that the true value of the Hubble constant. And this isn't particularly surprising because there are many galaxies within the sky localizations of some of these events, and the luminosity distance posteriors for each of these events, the true luminosity distance doesn't necessarily align with the peak at posterior. And so you end up getting quite a spread here, but the important thing is that when you combine all of these gravitational waves together, what you end up with is something that is actually quite constraining on the Hubble constant. This is all very well and good, but one of the major issues with this analysis is the fact that almost by definition, galaxy catalogues are not complete because EM telescopes are flux limited, which means that they only see things down to a certain brightness, depending on the strength of the telescope and the length of their observing time. So it means that there is some significant fraction of galaxies just do not end up being observed. And the question is, how do you compensate for that? For example, this is a figure from a paper talking about the GLADE catalogue. GLADE is a composite catalogue made up of lots of different surveys. And essentially, you can see that its completeness drops off with luminosity distance, also with redshift, obviously. And so if you don't include these EM selection effects, as you can call them, then it's very easy to end up with a biased estimate of the Hubble constant very quickly. So in order to account for this, we take it into account within the methodology itself by marginalizing over the probability that the host galaxy is or is not in the catalogue, where here G denotes the host galaxy is in the catalogue, and G bar denotes that it is not. So very briefly, to look at each of these terms, this first one here is just what I described a few slides ago. It's the gravitational wave likelihood, where you use the redshift prior from the galaxy catalogue. So it's just your sum over galaxies. These two terms here are just regular probabilities, the probability that a host is in galaxy catalogue or not, which kind of weight these two likelihood terms. They have to sum to 1 because the host galaxy has to be somewhere. And then the final term is the gravitational wave likelihood, assuming a host galaxy is outside the galaxy catalogue. And in order to actually practically compute these three terms here, which aren't solely dependent on the galaxy catalogue, you do have to start making some assumptions about the universe that we live in. For example, you have to make an assumption about the apparent magnitude threshold of the galaxy catalogue that you're using. You also will need to assume a general distribution of galaxies in the universe. That would usually be a uniforming co-moving volume distribution. And you also need to assume something about the luminosities of the galaxies in the universe. For example, you might assume that they follow some sort of Schechter function. So if you do this and then redo an analysis, I think first I'm going to show you a cool GIF that I like. This is simulated from the same mock gravitational wave data, but with simulated galaxy catalogues that have an apparent magnitude threshold such that I think 50% of the detected events didn't have the host galaxy within them. And I think this is just a nice demonstration of how the constraint on H0 changes as you add more events to it. It narrows very quickly at the beginning when you get a few sort of loud events that are quite constraining. And then as you add more events over time, it narrows and moves a little bit around the injected value of H0, but never becomes inconsistent with it. But the actual impact of incompleteness, you can also see here a lot of these events are tending to be flat. They start up in informative at the low H0 end, which corresponds to low redshift, which is where you have all of your galaxy catalogue information. But then at higher values of H0 corresponding to higher redshifts, where your galaxy catalogue is maybe less informative because it is less complete, these likelihoods become flatter. But this does not stop you from making a constraint on the Hubble constant. It just takes a little bit longer to constrain the higher end. And the impact of incompleteness is demonstrated here. Essentially, for the same set of gravitational wave events, if you reduce the completeness of the galaxy catalogue by changing the apparent magnitude threshold to exclude more and more of the galaxies, this demonstrates how your constraint on the Hubble constant changes. Effectively, it gets broader the more galaxies you're excluding. But even if you go down to the point where you only have 25% of the host galaxies in the catalogue, you still remain very consistent with the Hubble constant. And theoretically, in the extreme of a completely empty catalogue, you'd just get something relatively flat back, or at least in this simplistic case with these binary neutron stars. So that's all very well and good with mock data. In terms of measuring the Hubble constant with real data, I'll first look at the first two observing runs of advanced LIGO and Virgo. At those points, we measured, by the end of O2, we had measured one binary neutron star with an electromagnetic counterpart, which is excellent, 10 binary black holes, and in order to use the black holes for the cosmological analysis, two different galaxy catalogues were used. The first was the GLADE catalogue. This is the composite catalogue I mentioned, which has pretty much full sky coverage, which is why it was very useful. It doesn't go particularly deep in redshift, but its full coverage means that it was good for the events which covered large sky areas. And then there was also the DES catalogue, a public version of the DES catalogue, which is highly complete, but only covers a patch of the sky. And so there was one gravitational wave event that was localized mostly within this area. And so it was used to provide the best possible redshift information for that event. So I think this is a nice demonstration about how important galaxy catalog incompleteness is. So on the y-axis here, we have probability that the host galaxy is inside the catalog as a function of redshift, where these sloping curves correspond to the GLADE catalog here. This orange sloping curve corresponds to the DES catalog, and then the vertical lines you see here are at the median redshift for each gravitational wave event, which has been calculated assuming, I think, Planck cosmology. So these lines here would shift as you change the Hubble constant, but these probability of detection curves do not. Those are insensitive to the choice of the Hubble constant. And what you can see is that with the nice deep galaxy catalog, you've got like 100% probability that the host is in the catalog. It's definitely in the sample. Whereas for the other binary black holes, there's a few which have maybe 50% probability that the host is in catalog. And then quite a lot of the ones are higher redshifts have very little support from the galaxy catalog. So you'd expect to get a relatively uninformative contribution from those events. And if you actually look at the results from LIGO and Virgo's O2 cosmology paper, that's effectively what you see. So here on the left are the individual contributions from each event, the individual likelihoods, where this curve here corresponds to GW 170814, which was the binary black hole that used the DES catalog, the most complete catalog. And as you can see, it is the most informative of these events, and also has a peak around 70, which is very nice, but due to a cluster of luminous and dense galaxies at the appropriate redshift, whereas the rest of the binary black holes are less informative. And if you combine that measurement with the EM counterpart and binary neutron star measurement, you get a small but noticeable improvement to the result there. As I should say, for all this talk of dark sirens, the idea is, of course, to always make the most use of all the information available. If an event has an electromagnetic counterpart, of course, we're going to try and use that. And then the idea being to combine all of the measurements together at the end to get the best possible, most informative measurement on H0. So I've brushed over a lot of detail about what went into the analysis on the previous page, because it turns out there are a lot of things which make dealing with real galaxy catalogues more complicated than you might think. And not just the baseline fact that they don't contain all of the host galaxies. There's also the fact that they often have very large redshift uncertainties, because often the redshifts are photometric rather than spectroscopic measurements. This also means that at high redshifts, some of these redshift measurements may become unreliable. There may be unrealistic structure that comes comes in due to the way that these photometric redshifts were computed, which obviously you don't want if you're using this as a prior, because if your prior is wrong and you're using it for all your events, that could certainly be bad. There's also the fact that, this is a fun one, galaxy luminosities are redshifted from source frame. So it turns out galaxies do not emit uniformly in all wavelengths, and telescopes are only sensitive to whatever band they are observing in. And so what they observe is whatever light has been redshifted into that band by the time it reaches Earth. But if you want to do something like luminosity weight theory galaxies, to say more probable hosts are more luminous, and you want to say make that comparison in a specific band to be consistent across all redshifts, it turns out that you can't just use the magnitudes as given in the catalogue. You have to apply these things called K corrections to try and basically work your way back to what you expect the source frame luminosity of the galaxy in that band would have been if it had not been redshifted. And then there's also the elephant in the room, the fact that galaxy catalogue completeness is not actually uniform across the sky, which was what was assumed with the mock data earlier. And for the O2 data that I showed on the previous slide, it was assumed to be uniform within the sky area of each event. So each event had a slightly different completeness correction applied, but it was assumed to be broadly uniform within it. This is a number density map of the GLADE catalog, again, GLADE 2.4, where you can think of number density as a proxy for how complete the catalog is. So you can see that there's a big dark swathe that goes across the catalog here. That's caused by the Milky Way band. Obviously, you can't see through that very well. And then there are also these much lighter patches over here, which are caused by much deeper surveys that go up to higher redshifts. And so you have a much larger number of galaxies. So how do you deal with something like that? I should say that each of these things can be addressed and has been addressed already within cosmological analyses. You can marginalize over your redshift uncertainties if you assume, say, that they're Gaussian of shape. For unreliable redshifts, you can discard galaxies above a certain redshift as long as you also account for that when you're computing your out-of-catalog probabilities. Yeah, and I already mentioned the K corrections, but non-uniform galaxy catalog completeness requires a little bit of an extension to the methodology. First question, is it a good idea to assume that the apparent magnitude threshold is uniform in the sky area of an event? As an example, no, it is not. This is GW 150914, and it's 99.99% sky area. And as you can see, there is a huge variation from having absolutely no galaxies within its sky area to having hundreds of galaxies, with almost sort of maybe an order of magnitude difference between the sort of main two colors that you're seeing there. So clearly this is something that we would want to address, and is what some of my most recent work has been looking at. And one way to approach this is to take the methodology that we were working with earlier and apply it on a sort of pixel by pixel basis. So before you ask the question of what is the probability that the host is in or outside the galaxy catalog, you first split up the sky into a number of pixels. The higher number of pixels, the better resolution you get. And then you can consider each pixel on an individual basis and ask what is the probability, if the host galaxy was in this pixel, that it would be inside the galaxy catalog. And doing so, this is same gravitational wave event, same galaxy catalog, but just looking at it in terms of apparent magnitude threshold. And you can see the sort of coarseness of the pixels here, but how it describes reasonably well the sort of sharp kind of structure that you see due to the edges of different galaxy surveys overlapping. and also captures the dropping completeness you get around the galaxy, the galactic plane, where white here has essentially been considered to be completely empty. There are no galaxies that we can see here because it's entirely obscured by the Milky Way. So once you've done that, you can have a look at what is the probability of the host galaxy being in the catalogue for each pixel. I've demonstrated it here for 2 events. So this is very similar to the previous kind of plot. Probability host is in catalogue along the y-axis as a function of redshift on the x-axis. But now each of these sloping curves corresponds to a different pixel. The 50% most probable pixels within the event sky area are the orange curves. And the blue dashed line shows what you would have estimated if you assumed that completeness was uniform within the sky area of the event. So you can see that for some events, the average assumption has sort of overestimated how informative this event is likely to be, whereas for other ones, it has underestimated it. And the result of adding this new information into your analysis can be sort of seen if you look at individual gravitational wave events. So again, keeping my favorite 2 events. The plots here on the left-hand side are the sort of likelihood for each event. The blue shows the non-pixelated, assuming uniform completeness result, whereas the orange shows the pixelated completeness result. And the right-hand plot shows the individual contribution from each pixel, which I find to be really quite interesting, because when you're looking at events like GW 170608, which had reasonably high in catalogue probability, you can see that there's actually quite a lot of structure there within some of the pixels. And interestingly, you also end up getting some of that structure when you actually combine all of the pixels. It's much more informative than it was before. And I think this is interesting, though probably not significant, that it has a very small bump around a Hubble constant of 70. And the overall impact of making this switch from uniform to pixelated can be seen taking the sort of 01 and 02 events as a sort of baseline. If you do the same analysis with all of the same assumptions, apart from on how you're treating your completeness, essentially you get a sort of noticeable improvement going from non-pixelated to pixelated, maybe that of about 5%, which at the moment I would say is a very nice improvement. So that's all very well and good on the galaxy catalogue side, but I did sort of brush over the gravitational wave selection effects earlier. I just said that they are slightly complicated and said I would come back to them, which is what I'm going to do now. So the reason that gravitational wave selection effects are more complicated when you're dealing with the population of binary black holes is, as we just heard in the previous talk, the mass distribution of binary black holes is not currently very well known. It's not very well constrained. And the interesting thing about gravitational waves from compact binaries is that while there is mass information in the signal we get, it is the redshifted mass, not the source frame mass, that we are measuring, where the difference between the two is this factor of 1 plus z. So if your mass distribution happens to look something like one of these are all examples of potential mass models that could be used to describe the binary black hole population for the primary mass. If it has interesting features, where interesting means maybe sharp features like a turn on or turn off, or it has peaks or troughs, there's actually cosmological information to be gained purely from the mass model that you're looking at and the masses of the gravitational waves that you're detecting. Because essentially, when you get the detector frame mass of an event, in order to convert it into a source frame mass, you take the luminosity distance of the event that you've estimated, and you also need a cosmology, or a value of the Hubble constant. And so if you look at the population of gravitational wave binary black holes altogether, and you vary the cosmology that you're looking at, you can find distributions that match better or worse with your model, depending on the value of the Hubble constant that you choose. So in this paper by some of my collaborators, this was demonstrated very explicitly. They simulated about 64 binary black hole detections with sort of current detector sensitivities, assuming a power law plus peak mass distribution, and then used the gravitational wave data to jointly estimate hyperparameters for the mass distribution as well as cosmological ones. So, for example, mu g here refers to the position of the peak in the power law plus peak, so that would be where the Gaussian peak is essentially located, and M max is essentially the high mass cutoff. And what you see when you look at both of them is that there is correlation between these parameters and the Hubble constant, as you see from the fact that these contour plots are diagonal, they have some shape. Now, this is really cool. I think it's really cool because it essentially means that there is cosmological information just in the population of binary black holes. I'm going to say you don't need galaxy catalogues, but there is additional information there which isn't dependent on galaxy catalogues, which is great for using for basically including more cosmological information. However, it also comes with a downside, and that downside is if you assume a mass model with fixed parameters and it is incorrect, you will end up biasing your result, as demonstrated here by two plots where here M max has been fixed different values. I think the correct one is 85. But if you fix it to values away from that, you end up with a constraint on the Hubble constant, which does not match so well, or is in some cases completely inconsistent with the true value of the Hubble constant. And there's a similar, although less dramatic effect in the position of the mass, the Gaussian peak. And the reason that this is potentially problematic is that current cosmological analyses using the galaxy catalogues assume a fixed mass distribution for the simple fact that it is computationally costly, currently a little bit intractable, to jointly estimate cosmological parameters and mass hyperparameters while also using galaxy catalogues as prior redshift information. But before I go on to the end, recently, last week, cosmology results came out for the third gravitational wave transient catalogue, which used the methods that I have described in my presentation today to make a measurement of the Hubble constant. So this is one of the main results from that paper. I can encourage you to go and have a look. And essentially here, dashed orange line shows the contribution from all of the binary black holes and, well, binary black holes, neutron star, asymmetric mass, all of the events which are not the binary neutron star with its counterpart. The black is the binary neutron star with its counterpart, and the combination of the two is this blue line here, which you can see is far more informative. It is a much tighter constraint. However, this result also comes with the caveat that it has a fixed mass distribution inside it. And so, as you can see with the dotted line here, you get quite a strong contribution just from the binary black hole mass distribution, which is a stronger contribution than you would expect if you were, say, marginalizing over the hyperparameters of the mass distribution or jointly estimating them at the same time. So that's pretty much where we are at the moment, with results hot off the press. And the challenges that remain, that this is a non-exhaustive list because I'm sure there are many challenges that remain, both on the galaxy catalogue side and the gravitational wave one. On the galaxy catalogues, we need to be able to find galaxy luminosities and redshift estimates that are valid at higher redshifts so that we can make the most of the high redshift events that we detect. Also, the luminosity function has redshift dependence, which should also be taken into account as you're detecting events at higher redshifts. The gravitational wave side, obviously, incorporating or marginalizing over the uncertainty in population hyperparameters is going to be a very important aspect to this analysis over the coming few years. So when do you think we will have an answer? Usually I am very hand-wavy when it comes to something like this, and I will continue to be hand-wavy. When will we measure the Hubble constant well enough to determine who is right, whether it's low H0 or high H0 systematics or an inaccurate model? And I'm going to say it really depends. It depends on a lot of things. It depends mostly on the quality of events that we get over the next few observing runs. I will say that it looks positive though, because we have more gravitational wave detectors coming online. CAGRA joined the network at the end of 03, and so its presence in 04 should make a very big difference to better localizing events. We're also expecting deeper galaxy surveys with better redshift estimates to become available in the next 5 years or the next decade, which means you can get a much more informative contribution from your individual events. So I'll say, in any case, the next 5 years should be interesting, so keep an eye out for developments then. And finally, just to conclude, basically, a lot of progress has been made to using gravitational wave dark sirens for cosmological measurements, both on the galaxy catalogue side and the gravitational wave population and selection effect side. But there are a lot of challenges remaining on both of those sides, which hopefully we will be able to address in the next few years before all of the fantastic constraining data arrives. Thank you very much. I will leave it there.